Okay, so we're going to finish this off by doing application problems. So this is going to be applications of exponential growth and decay. So this is going to seem kind of familiar to you. So we're dealing with population growth. We're dealing with something that grows continuously. So we're going to have this E here. So the function pt equals p sub 0 of e to this kt. Remember, k has to be positive because we're going to use positive percents for growth. Is going to be population growth. So in this function, or sorry, let's try this again. P naught is the population of this function. PT is the population after time t. T itself is just time, and k is your exponential growth rate. So you want to make sure your growth rate is in the same unit as your time. Okay. And then once again, because it is p sub 0, p sub naught, that is your initial population that you're going to start with. So what we should always see with population growth, like I said, because at a time 0, so the beginning of our function, we should get p sub 0 is what's going to be left over. So that's what we're expecting, is that every time that we have a population growth, that the x-intercept, sorry, your y-intercept should always be p sub naught, or p sub 0. So for our first example, in 2009, the population of Mexico was about 1,000, sorry, that's not 1,000, 111.2 million people. The exponential growth rate was 1.13% per year. We want to find the exponential growth function, estimate the population in 2014, and then find out how long will it take for that population to double. Okay, so just giving myself a little extra room here. So some things to point out. The population growth formula was PT, P subscript 0, E to the KT. So what we have here is that we know the population in 2009 is 111.2. That is our P naught. That's our original population. The exponential growth rate is 1.13%. So I need to convert that into a decimal. So that's actually 0.0113. So for A, our formula is going to be PT 111.2 E to the 0.0113 T. So if we want to estimate what the population is in 2014, remember this is all starting in 2009. So if we want to figure out what T would be, T would have to be 2014 minus 2009, since that was my initial starting period. So this means I want to know what the population is 5 years from 2009. So we're going to have P to the 5th is equal to 111.2 exponent, or E to the exponent. If you're going to put this in your calculator, try to put your exponents in parentheses here, just because it's going to save you some problems. But we have 0.0113 times T, which is going to be 5 now. Okay. So if I 111.2 E to the 0.0113 times 5. A second. Something on my calculator did not go where it was supposed to. Times 5. No. There we go. Sorry, it was just being a pain. What we're going to see here is that we are going to get 117 point, we round to one decimal place, 77.7. So in 2014, we expected to have 117.7 million people. So we're going to do pretty much all of the C over here. So let me explain C. So C is asking how long until my population doubles what it was in 2009. So in 2009, we know that it is 111.2 million. Well, if I double that, I'm going to have 222.4 million. So what this is going to be is going to be my PT. So what I have here is 222.4 should be equal to 111.2 e to the 0.0113 t. T is the one thing I don't know. So I want to know how long until that population doubles. So I'm going to solve for t. So to use any of those rules that we learned about solving with exponential functions means I need to isolate that e to the 0.0113 t. So to do that, I'm going to divide both sides. There we go. Using one of my twos. I'm going to divide both sides by 111.2. Sorry, I was trying to type, put that in there and talk at the same time. So what's going to leave me with on this side is that's just going to leave me with 2. And I'm going to have e to the 0.0113 t. So going back to some of the ways we were handling this, we can't put 2, right? So it has a exponent of, so it's not an exponent of, I think, exponent of the natural number. That's what I'm trying to say. But what I can do is, because I have this base e here, is I can take a natural log of both sides. And it's going to cause this to disappear, and I'm just going to be left with the 0.0113 t. And I still have natural log of 2 over here. So if I just want t, that means I just had to divide both sides by 0.0113. So t, I better actually move t here. What t turns out to actually be is the natural log of 2 divided by 0.0113. So I'll put this in my calculator. Natural log of 2 divided by my rate of 0.0113, I'm going to get approximately 61.3. So it's going to take approximately 61.3 years from 2009 for the population to double. So what we think here is that the population will double between, if I add down that 61 to 2009, it should double somewhere between 2070 and 2071. So your worksheet problem, worksheet 16, E. coli has a doubling time of 20 minutes, which means that it has a growth rate of 3.5% per minute. A colony of E. coli on an agar plate currently has a colony count of 500. So just like before, we're counting a population. We want to figure out what the population growth function is, estimate the colony count after 2 hours. So remember, we're doing the rate in minutes, and then we're asking 2 hours, so you have to rectify that. And then how long will it take for the population to triple what it currently is? So take a moment and do that, please. All right, so the doubling time, we don't have to really worry about that so much, because where here is telling me the growth rate. In here is telling me my population. So the initial population is going to be 500, a colony count of 500, and my rate is going to be 0.035. So for A, my formula is going to be P to the T equals 500 E to the power of 0.035 T. So for B, we want to estimate the colony count after 2 hours. But remember, we were measuring our rate in minutes. So I have to take 2 hours and turn it into minutes. So there's 60 minutes in each hour. So 2 hours is actually going to be 120 minutes. So that's what T will be. So I need to figure out what T of 120 is. So we have 500 E to the 0.035 times 120. So remember, keep your exponent in parentheses with calculators. It depends on the calculator, but some of them you're really going to need to use those parentheses to make sure it works correctly. Okay. So 500 e to the x of 0.035 times 120. There, I got one of those janky calculators I keep telling you about. This is going to be approximate population of 33,343, let's say 0.2. So for us, we might just say this because we're not like counting in millions or anything. If you wanted to, because we got a point, we'll just round this up. So just to be safe, to make sure we don't have a partial bacteria here, it's going to be 33,344 colony count. All right, so to do C is tripling time. So if I triple my population, I'm started at 500 and I triple it, that's going to be 1,500. So C is going to be 1,500 equals 500 e to the 0.035 t. So we want to figure out how long it triples, so we're going to solve for t. So first thing we're going to do is divide both sides by 500, so we can get that e by itself. So that is 3 is equal to e to the 0.035 t. So if you notice what's happening, like with both of these, I get left of this e to the kt essentially. And this side is just whatever. So if we were doubling, it's 2. We're tripling, now it's 3. Just pointing this out because we're going to use this to save ourselves some work later. So we just need to take a natural log of both sides because we're trying to counter this base e. And we're going to be left with natural log of 3 is going to be equal to just 0.035 t. So my t, if I divide both sides by my 0.035, natural log of 3 divided by 0.035. Take a little over 30 minutes. I need to get the exact number here. So it's going to be natural log of 3 divided by 0.035. So it's going to take roughly 31.4 minutes for this population to triple. So like I said, double time, so it's going to take 20 minutes for it to double. But after that, it's just going to take an additional 10 minutes to triple. Or initial 11, 12 minutes to triple. So bring this back to continuously compounding interest, is we can use something similar for that formula. So this is actually pretty much the same formula as we had made before, the PRT. It's just in this case, instead of having AT, we have PT. So PT is your balance in your account after T years. P sum naught is just your principal. So it's the amount that we invested initially. T is going to be in years, and K is your interest rate that we're compounding continuously with. So knowing that, your next worksheet problem is, suppose that $2,000 is invested at an interest rate of K compounded continuously and grows at $2,504.65 after 5 years. So notice we were not given an interest rate. So what you're going to be looking for, you have everything to find interest rate. Then you're going to find your exponential growth function, find out what the balance would be after 10 years, and then figure out how long it takes for your investment to double. All right, so like I said, just a slight tweak on this. So we are told our initial amount that we're investing. We are told how much we expect to have after a time t. We're told that t is going to be 5. So what we have here, $2,504.65 is equal to $2,000 e to the 5k. So remember, we got t, which is 5 years. It's k that we don't have. So in this case, we solve for k to get that interest rate that we need here. So we're going to initially divide both sides by $2,000 to get that e by itself. So I'm going to change this over here. So we got e to the 5k is going to be equal to 2,504.65 divided by 2,000. I'm going to leave it like this just so I can avoid some rounding errors at the end. We need to do a natural log of both sides. So we can take care of this base e and we can get that exponent down. We have to make sure we do it to the other side as well. So natural log on both sides. We know that's going to leave me with 5k is equal to natural log of 2,504.65 divided by 2,000. So if I just want my k, my interest rate, that means I had to divide by 5 here and divide by 5 here. So it's going to be natural log. So I'd keep this all in parentheses when you do this natural log. And then remember to move outside the parentheses to divide by 5. Okay. I think I remember what this number was, but let me just double check. Yeah, so this is approximately 0.045. So what my interest rate is really, it's about 4.5%. Okay, so B, this was A. B just wants my formula. So P to the T is actually 2,000 E, and now we have K, which is going to be 0.045 times T. So C is just, we need P to the 10. So let me get that quickly. 0.045 times 10. So PT is going to be approximately $3,136.62. So after 10 years, we expect that $2,000. If we put that $2,000 in the account after 10 years, we should be seeing about $3,136.62. So my very last problem is, once again, I'm just asking how long for this to double. So we know, as we've seen over and over again, what's going to happen here is that if I want what's going to double to, I'm just going to have 2 is equal to e to the 0.045 t. Sorry, I had to move something out of my way. Like I said, we kept seeing this pattern happening, so we're going to kind of cut to the chase here. So if we do the natural log of both sides, what we can see here is I could have just easily skipped this natural log part on this side and just said 0.045 t should be equaling natural log of 2 if I want that doubling time. So t is just going to be that natural log of 2 divided by your interest rate. So what we're going to get here, natural log of 2 divided by 0.045 is going to be 15.4 years.